Welcome to The Mathematicians Podcast, the podcast where we follow the fascinating stories behind the people that count in the history of mathematics. I'm your host, Benjamin Cornish, and today we'll be looking at the points of the life and work of one of history's most intriguing polymaths, Democritus of Abdera. I want you to imagine a bustling village market. Picture it, vendors shouting about their fresh produce, children darting between stalls, and the ever-present sound of animals bleating, clucking, and braying. Now, amidst all this chaos, there is a man, a curious sort, standing near the fountain at the centre of the square. He's watching the crowd with a sly smile, occasionally chuckling to himself. Why is he laughing? Well, that's exactly what everyone else in the market is wondering. To them, there's nothing particularly funny happening. No one slipped on a banana peel. No chicken has run off with someone's bread. But this man, with his sharp eyes and even sharper mind, seems to find the entire scene utterly hilarious. Now, this isn't just any laugh. It's not loud or boisterous. It's quiet, thoughtful, as if he's amused by some grand cosmic joke that no one else has noticed. One of the vendors, tired of the mystery, finally approaches him and asks, "What's so funny?" The man turns, his eyes twinkling, and says, "Everything." Naturally, the vendor is baffled. "Everything," he repeats. "What do you mean, everything?" So the man explains, or tries to. He points out the way people haggle over the price of apples as if their lives depend on it, only to splurge on sweets a few stalls over. He describes the absurdity of a goat chewing on a piece of paper while its owner desperately tries to retrieve it. He even notes the way the cobblestones in the square seem to be arranged just irregularly enough to trip the occasional passer-by. "To me," the man says, "the world is like a giant puzzle, and the more I look at it, the funnier it gets. Not because it's silly or meaningless. No, it's funny because it's so wonderfully, endlessly complex. And that's what makes me laugh, the sheer brilliance of it all." But here's the twist. This man isn't content to laugh and leave it at that. No, his laughter is just the beginning. It sparks a question that will haunt him long after the market has emptied and the sun has set. Why is the world so complex? What's behind all these patterns and behaviours that we take for granted? And most importantly, is there some hidden order, some deeper truth that makes sense of it all? The man in this story? Me, as it happens. Before becoming a maths teacher, I had a brief stint as a stand-up comedian. My big article of observational humour? You know what's funny? Everything! Now, at this point, I was intending to return immediately to the mathematics. However, one thing I learned during my Comedy of Mathematics module at university is that everything funny comes in a triad, or threes. So, it would be remiss of me not to tell you two more of my other jokes of my own creation. I studied Spanish as a child. I got a grade C, or as they would call it, a yes. I left a very mediocre review on TripAdvisor for the Orion's Belt constellation. 3 stars. Pause for laughter, edit that to make it funnier, and here we go. Naturally, it was a brief stint as a stand-up comedian, and I instead returned to my maths degree. But this man laughing in the market could have been anyone. More relevant for today's episode, it could have been Democritus. Known widely as the laughing philosopher, Democritus's infectious curiosity and groundbreaking ideas left an indelible mark not only on philosophy, but also on mathematics. He very literally shaped the building blocks of modern scientific theory: atoms. He was a man ahead of his time, bridging the abstract world of atoms with practical geometrical insights. But what exactly were his contributions to mathematics? And why was he always laughing? Well, today we'll uncover his story, a mix of intellectual daring, deep thinking, and yes, humour. Let's start by stepping back over 2,400 years into the bustling world of ancient Greece, still in modern-day Greece, in the part that is now below Bulgaria, born around 460 BCE in the city of Abdera in Thrace. Democritus lived during a time when intellectual traditions were flourishing. Abdera itself was somewhat of a cultural backwater, a small city along the northern Aegean coast, but this didn't stop Democritus from thinking big. He travelled extensively, journeying to Egypt, Persia, and possibly even as far as India. These travels exposed him to diverse cultures and the intellectual treasures of ancient civilizations. Imagine him poring over Egyptian papyri on geometry, trading ideas with Persian scholars, and perhaps marvelling at the architectural ingenuity of distant lands. Democritus was no ordinary philosopher. He sought to understand the world's fundamental truths, whether they lay in the cosmos, the structure of matter, or the pattern of mathematics. Now, let's focus on his mathematical contributions. While Democritus is more famous for his atomic theory, the idea that all matter is composed of indivisible particles called atoms, he also explored mathematics with remarkable depth. He's credited with early insights into geometry and the concept of infinity, both of which were extraordinary for his time. One of his most significant contributions was his work on the volume of shapes, particularly cones and pyramids. Democritus was among the first to assert that the volume of a cone is 1/3 the volume of the cylinder with the same base and height. An invaluable insight for my summer job as an ice cream man. To modern listeners, this might sound straightforward, but in the 5th century BCE, it was known that a triangle had 1/2 the area of a rectangle, but the cone was revolutionary. He lacked the tools of calculus that we have today, yet he intuited the relationship using purely geometric reasoning. We do not have his original notes to decipher his technique, but perhaps we can guess at it. Democritus considered the thinnest layers of various solids, which were termed laminae. These laminae could be put together to get back to the solid. Now, there was some contradiction there. Will the laminae of a cylinder match the laminae of the cone? If yes, then how can the cone differ from a cylinder? If no, then how can the atomic laminae differ? Paradox. So, what other laminae were well understood? Well, we know from Ames, back in episode 1, that the volume of a pyramid was well understood to be 1/3 that of the cuboid. In fact, this doesn't need to be calculated with calculus. We can cut it with a cube. Start with a cube, select one vertex which will serve as the apex of all 3 tetrahedra, move across all 3 edges from this vertex and label the results ABC, then cut 3 tetrahedra with ABC as complete right angles. The result will be 3 congruent tetrahedra. Thus, the area of each is equal to 1/3 the total. I mean, simple. Now then, we need to analogize the cone to the tetrahedron, and the cylinder to the cube. For this, we make use of the old squaring the circle trick. That is, to imagine a cube with the sides of length root pi and the same height as the cylinder. Democritus argued that the laminae of the cone will each be a circle, and thus it differs from the cylinder by having this stepped edge rather than a smooth one. But then each circle will have the same area of a corresponding square in the tetrahedron using the rule of proportionality, and thus the ratio of their respective volumes must be the same. Interestingly enough, this is the same answer I give in class when my students ask me. It neatly sidesteps having to go into any calculus. Democritus's work was the base layer of a cone for a later apex mathematician like Archimedes, who would formalise these principles. Archimedes himself praised Democritus, calling him a visionary who touched on the truth but did not fully prove it. It's worth noting that much of Democritus's mathematical work is lost to history. We know about it primarily through secondary sources like Aristotle's Critiques and Archimedes' Admiration. This fragmentary record only adds to his mystique. Why was Democritus called the laughing philosopher then? Ancient accounts tell us that he was known for his cheerful disposition and his tendency to laugh at the absurdities of human behaviour. In a world full of war, political intrigue, and existential despair, Democritus found joy in understanding the universe. His laughter wasn't dismissive, but rather a reflection of his belief that a deeper understanding of nature brought clarity and peace. Imagine Democritus walking through the streets of Abdera, observing people argue about trivial matters, and chuckling to himself. He might have thought, if only they understood the infinite nature of the cosmos, they wouldn't be so concerned about small things. After all, compared to the infinite, everything else tends to zero. One anecdote tells of a time when his fellow citizens thought he had gone mad because he spent days dissecting animal eyes to study vision. When they asked what he was doing, he reportedly burst into laughter and explained that he was unravelling the mysteries of perception. This curiosity-driven humour defined his approach to life. Democritus proposed that the diversity of objects in the world can be fully explained by the properties of atoms in combination. He likened this to the letters of the alphabet, which, though limited in number, can produce an almost infinite array of words through differences in shape, arrangement, and orientation. For instance, the shape of the letter, like A compared to N, its arrangement in a sequence, AN versus NA, and its positional arrangement, N flipped to resemble a Z, determined its role in a word. Aristotle, who recorded this analogy, used terms like schema, or shape, taxis, arrangement, and thesis, position. You might recognise the words schema, taxis, and thesis from modern language as well, though Democritus likely had a more dynamic understanding of these differences. Interestingly, Democritus omitted size from this particular analogy, perhaps because it didn't fit neatly into the metaphor of alphabetic letters. Yet he made it clear elsewhere that atoms also differ in size, further contributing to the multitude of differences we observe in macroscopic objects. Democritus's ideas about atoms extended to the nature of perception. In a famous surviving fragment, he argued, "By convention, sweet. By convention, bitter. By convention, hot. By convention, cold. By convention, colour. But in reality, atoms and void." This suggests that qualities like taste, temperature, and colour are not inherent to the atoms themselves, but arise from their arrangement and interactions with our senses. Democritus's phrase, "by convention," doesn't imply arbitrariness, as some might think. Scholars like David Furley argue that Democritus meant these sensory experiences are consistent and reliable, but are relational rather than intrinsic properties of matter. In essence, sweetness exists not in the sugar atoms, but in the relationship between their arrangements and our perception of them. Modern interpretations, like those of Alexander Morelatos, frame this distinction as one between intrinsic properties, the actual shape, size and motion of atoms, and relational properties, the ways atoms interact to produce phenomena like colour or flavour. This insight foreshadows later philosophical debates about primary and secondary qualities, ideas that would influence thinkers like Galileo to Locke. This view of perception also complements Democritus's atomism. The universe's complexity emerges from the simple yet versatile properties of atoms, like letters forming words. The infinite combinations of atomic properties explain everything we see, taste, and touch. Again, this might feel a bit too much like physics, but consider this as a very early appreciation of the study of combinatorics. While we don't have any formal definitions or formulae, we clearly have a dedicated thought to its existence. This was a mirror for our own study of maths in the modern day. We often have an idea about how something might be described without quite being able to describe it. Sometimes the language can come centuries later. For instance, if we feed too much sugar to a ball, it could become a hyperball. At this point, I might point you towards the Poincare conjecture. Loosely described, it concerns loops in four-dimensional hyperspace and whether the property of a closable loop necessitates the triviality of the fourth dimension, and generally speaking, the loops are not so loose. I hope you have a matrix transformation in the form K001, because this next interpretation is a bit of a stretch. Democritus explained perception through the concept of eidola, thin films of atoms that are constantly shed from the surfaces of objects. These atomic layers travel through the air and, if sufficiently compacted, interact with our sense organs to produce sensory experiences. The gradual erosion of objects over time served as empirical evidence for this process. As eidola move through the air, they are subject to distortion from collisions with other atoms. especially over long distances, which explains why objects appear differently depending on their proximity to the medium through which they are viewed. A complementary explanation suggests that Iodola impress the air, compacting it in a way that conveys the object's properties to the observer. In both accounts, visible qualities like size and shape are transmitted through these atomic interactions. Democritus also extended this principle to other senses, such as taste. For instance, he argued that the different taste sensations arise from the specific shapes of atoms contacting the tongue with certain shapes corresponding to sweet or bitter flavours. Now, you might assume that I've gone walking in the woods here, but bear with me. I could easily argue that this insight is a precursor to information theory. Again, not written in any formal language, but there's clearly a recognition that information can be assigned unit form and transmitted, altered, or lost. Specifically, the information can be lost whilst the atom or carrier itself remains. In ancient atomist theory, there is a debate about whether atoms move due to intrinsic weight or external forces. Some scholars of the philosophy argue that the main theory is the weight arises not from the atoms themselves, but from the cosmic whirl's centripetal forces. This cosmic whirl being the general movement of the entire cosmos. Others suggest atoms might possess a natural vibratory motion, though evidence of this is unclear. It does sound a lot like Brownian motion, though. Primarily, atomic motion is driven by collisions, where mutual resistance causes atoms to rebound away from each other. Aristotle criticised Democritus for failing to explain the origin of motion itself, focusing only on how collisions direct movement. But hold on a moment and consider the implications of this thought. Consideration was made for intrinsic forces, which we still consider to be intrinsic to matter. Moreover, we now believe that every single atom has an intrinsic relationship with every other atom in the universe in the form of a gravitational attraction. Or the thought of an intrinsic vibration. Again, this predicts our modern understanding of what thermal energy is. We also have a suggestion of the understanding of centripetal forces and a deep consideration of collisions and the potential for mechanical determinism. Unlike modern mechanistic or inertial views of motion, ancient atomists saw motion in more dynamic and context-dependent terms. Let's turn to one of the most profound questions Democritus tackled, the origin of motion and the concept of initial causes. His atomist theory is often viewed as deterministic, that is, everything that happens in the future results from the collisions and interactions of atoms in the past. But this raises a significant question. Did the universe have a beginning, or has it existed eternally? Now, Democritus believed that the motion of atoms was eternal, with no initial mover or starting point. For him, the cosmos was an endless cycle of atomic collisions, separations, and recombinations. Aristotle criticised this view, arguing that it failed to explain why motion existed in the first place. If every atomic movement is caused by a prior collision, then what initiated the first collision? This deterministic view implies a universe governed entirely by the laws of nature, having little room for randomness or divine intervention. However, Democritus's atomic model also suggests that a cosmos that doesn't require an external creator, a radical idea for his time. The universe, in his view, simply is and always has been driven by perpetual interplay of atoms. Now at this point, the argument starts to become a little bit more philosophical, but let's weigh in on the mathematics behind what both sides of the argument are suggesting. Democritus and the determinists argue that everything must have a cause, and therefore, by inductive reasoning, they can trace the origin of all things infinitely far back to no fixed origin, which is a circular argument to suggest then that nothing as a system has a cause. In other words, the entire system of the cosmos was not caused, and yet everything inside the cosmos must have been caused. This is where the argument has the logical fallacy. whereas the criticism of Democritus' work suggests that everything except one thing must have a cause, and that one thing is the first cause, or the primary mover, where everything follows on from the primary mover. And the logical flaw on this argument might be, well, why is it that this first cause doesn't require a cause? And here we are somewhat begging the question by trying to suggest that everything needs a first cause, where this primary causa just does not require a cause. Now, that does sound a little bit wordy when we discuss it, so let's think about it in a mathematical context as an inductive reasoning. An inductive proof must have the statement that if it is true that n is equal to k implies that n is equal to k plus 1 is valid, and if it is also true that n is equal to 1, then it can be demonstrated that n is true for all values of n. This is certainly the form of the conclusion that I teach my students for their exams. However, this implies that there must be a first base case that is considered valid, the n is equal to 1 case, on which the inductive reasoning is begun. A little bit like a chain of dominoes that all fall over if the one next to it falls over, but you still need to poke the first one over for it to cause that inductive chain of argument. Well, Democritus' view here is like suggesting that if n equals k implies n equals k plus 1 is valid, and therefore if n equals some arbitrary p is valid, then it can be demonstrated that n is valid for p minus 1, p minus 2, p minus 3 ad infinitum. It's almost like applying the law of induction in reverse. Modern interpretations often compare this idea to scientific concepts like the conservation of energy or the Big Bang theory. While the Big Bang suggests a starting point, Democritus' eternal cosmos challenges us to think about the nature of beginnings themselves. Is the beginning necessary, or is existence itself infinite and self-sustaining? It is starting to feel like this particular episode on Democritus is infinite and self-sustaining. Now, I appreciate that this is meant to be a podcast about mathematics, not philosophy or theology, but it's very difficult to split these schools of thought when discussing the ancients. What I think we should remember is that the lines of inquiry we make into the world of maths and science are led by our expectations of what we might find. For many mathematicians of the age, the notion of an actual infinity was impossible. So, whilst the universe may last forever in the future, this is only a potential infinity. But there must have been a starting point. It will be important to keep this in mind when looking at the modern mathematicians working on subatomic particles, stochastic mechanics, and anything quantum. You can't find the answers if you're unwilling to ask the questions. I have found my own views on mathematics have changed since I transitioned from being intensely religious into an atheist. Consider, for instance, the numerical constant pi. Is this value necessary and fundamental to the universe, or destined by the whims of a creator god, and thus could it have been different? I'm not arguing that philosophy and theology have a big place in mathematics, but clearly mathematics has a big place in theology and philosophy. So I shall permit myself from time to time to talk about the philosophical implications of mathematical arguments. Another fascinating aspect of Democritus' mathematical thinking was his engagement with this concept of infinity. While the Greeks were often uncomfortable with infinity, seeing it as paradoxical and even unsettling, Democritus embraced it as a useful tool for understanding the universe. He theorized that space and matter were both infinite. In mathematics, this led him to consider problems involving infinitely small divisions. For instance, he speculated that a line could be divided infinitely into smaller and smaller parts. This idea wasn't just philosophical, it hinted at integral calculus, a field that wouldn't emerge for another 2,000 years. Think about this. Democritus' atomic theory proposed that matter was made up of tiny indivisible units, while his mathematical idea suggested that space and magnitude could be divided infinitely. So how did he reconcile these seemingly contradictory views? Scholars believe that he saw atoms as building blocks of the finite world, and infinity as a property of the conceptual mathematical realm. This duality showcased his ability to think abstractly while remaining grounded in physical reality. It begs the question, is mathematics a model of the world, or is mathematics the world? It also links back to what we discussed in episode 6, with Hippocrates and mathematical accuracy being different to physical accuracy. Beyond his intellectual pursuits, Democritus was also known for his aesthetic lifestyle. He inherited a significant fortune, but chose to live simply, investing his wealth in learning and exploration. He's said to have spent so much on books and travel that he ran out of money and had to rely on the generosity of friends and patrons. One story tells of Democritus's encounter with Hippocrates, that's the medic Hippocrates. The people of Abdera worried about Democritus's odd behaviour, laughing at seemingly inappropriate times and studying obsessively. They called in Hippocrates to diagnose him, and after spending time with Democritus, Hippocrates reportedly declared that the philosopher was not mad, but possessed of extraordinary wisdom. This story highlights the tension between genius and societal norms. Democritus's relentless curiosity and unorthodox methods set him apart, often making him a figure of both admiration and misunderstanding. Now, I'm sure that working outside of societal norms is not something that mathematicians will become known for to this day, however. As we wrap up, let's consider Democritus's legacy. His work in mathematics, while overshadowed by his atomic theory, influenced further thinkers profoundly. Archimedes, Euclid, and even early pioneers of calculus owe a debt to his insights. His laughter, meanwhile, reminds us of the importance of joy in intellectual pursuits. I myself have felt emotion when conducting mathematics. Not easy for a British man to admit to, but the joy of discovering a new fractal, the pain of completing a series of mathematical modelling only to realise you had an early sign error in a derivative, the relief of pages and pages of expressions cancelling down to a neat single fraction. What can we learn from Democritus today? Perhaps it's that curiosity and humour are as essential to understanding the universe as rigour and logic. Whether you're a mathematician, a teacher, or just someone who loves a good story, Democritus's life offers inspiration to explore, to question, and yes, to laugh. Thank you for joining me on this journey into the life of Democritus of Abdera. If you enjoyed today's episode, don't forget to shed off the most external layer of your atoms so that your friends can also enjoy it. Or perhaps just subscribe and share to the Mathematicians podcast. You can also follow the pod on Instagram at mathematicians.pod for slightly less serious content. Next week, we'll be having a general discussion about Archytas of Tarentum. I hope I can move you to listen along. Until then, goodbye. The music today is Danse, Macabre Finale by Kevin MacLeod. You can find more information in the show notes.